Welcome aboard. You're flying with Captain Tass, your trusted guide through CPL and ATPL theory, straight from the Oxford Standard. Clear, concise, and exam ready. Let's get airborne. So, today's topic is great circles, rhumb lines, and directions on the Earth. So, let us begin by defining what a great circle is. Any circle on the surface of the Earth whose radius and center are the same as that of the Earth is called a great circle. So, as shown in the photograph, since the number 1 radius and number 2 center is the same as that of the Earth, it is called a great circle. A good example of a great circle is the equator. The shortest distance between 2 points on a great circle will be the distance between the shorter arc between those 2 points. If you're given 2 points on the surface of the Earth, you can only make one great circle that joins both of those points unless the points are diametrically opposite, meaning if this is the Earth, one point is over here, the second point is over here, and you can make infinite number of great circles that join these two particular points. A good example to imagine this would be if you're given 2 points, say the North Pole and the South Pole, and the pairs of meridians or pairs of longitudes that join both of these points, there can be infinite number of them, and all of them are great circles. The next point we are going to discuss is the rhumb line. A rhumb line is a regularly curved line on the surface of the Earth. The important thing to remember is that a rhumb line will cut all the meridians at the same angle. That is, it is a line of constant direction. As illustrated in this photograph, the red line is the rhumb line track as it cuts all the meridians at the same angle, and the blue one is the great circle track. Now, the rhumb line was traversed in earlier times when people did not have sophisticated navigation equipment like we have today, so they had to follow a constant heading or a constant direction during navigation. But we have a track that is shorter than a rhumb line track, which is called the great circle track. Now, if we come to the great circle track, on the surface of the Earth, a rhumb line will look curved, and a great circle track will also be curved, but it will be concave to the rhumb line. The rhumb line will be closer to the equator, and the great circle track will be closer to the pole. If we look at this illustration now, this is a chart which shows the distance or the track between Moscow and Vancouver. The red line is the rhumb line track, which on the chart appears as a straight line since it is of constant direction. However, on the globe, it is a curved line and covers more distance. On the chart, the blue line, that is the great circle track, appears as though it covers more distance. However, on the globe, the great circle track is less curved than the rhumb line track and covers less distance. Hence, today's modern navigation equipment, because of their abilities, allow us to traverse the great circle track, hence covering less distance. Now, some examples of rhumb lines are parallels of latitude, since all of them cut all the meridians at the same angle, or a particular latitude cuts all the meridians at the same angle, that is 90 degrees. A special case of a rhumb line and a great circle is the equator. The equator is the only a line on the surface of the earth that is both a great circle as well as a rhumb line. Meridians are semi-great circles and rhumb lines since they all have constant direction that is 0 degrees. As we discussed, the rhumb line between 2 points will always lie nearer to the equator, that is, it will be convex to the equator, and the great circle will be concave to the equator and will lie closer to the poles. The equator and any meridian along with its anti-meridian are both great circles and rhumb line tracks. Let us jump to great circle directions. Since we saw on the chart the rhumb line track is a straight line, however, the great circle track has a change in direction. Hence, we capitulate it with this particular diagram, where, as given in the northern hemisphere, if you are following a rhumb line track of 0, 9 or 0, your initial direction will be 0, 3, 0, that is less than your rhumb line track. In the middle, it will be parallel or equal to your initial direction, and towards the end it will be more than that of the initial direction. So let us name these points A and B. So while traveling from A to B, if you have a rhumb line track of 0, 9 or 0, your great circle track will initially be less than or decreasing than the initial rhumb line track. In the middle, it will be equal, and towards the end, that is towards B, it will be more than your initial rhumb line track or increasing. This is for the northern hemisphere. While traveling either from west to east or east to west. Now if you're traveling westwards from B to A on an initial track of 270 rhumb line track, the great circle track initially will be more, that is, it will be the reciprocal of 150, that is 330. Towards the middle, it will be equal, and towards the end, it will be 210, that is less than your initial track. Now, if we come to the southern hemisphere, as we can see in the illustration, initial rhumb line track, let's say again we're traveling from A to B, is 090. Initial great circle track will be more than or increasing than your rhumb line track, that is given by 50. In the middle, it will be the mean or parallel or equal, and towards the end, it will be less or decreasing. If we travel from B to A on a rhumb line track of 270, initially your great circle track will be reciprocal of 030, that is 210. So hence less. In the middle, it will be equal, and towards the end, it will be 330, that is more. Hence, this rule applies traveling both westwards and eastwards in the northern and southern hemisphere. It can be summarized using this diagram where it is shown that on a westbound track, initially it will increase, then it will decrease. On an eastbound track, vice versa, and similar for the northern and southern hemisphere. Hence, it is given by DIID. Let's jump to our next topic, which is distance on the earth. So over here we are introduced to the definition of a kilometer. A kilometer by convention is 1000 meters. But by definition, a kilometer is 1 by 10,000 into the distance between either pole and equator. So if this is the Earth, this is the equator, this is the line joining the poles, this distance divided by 10,000 will give us 1 kilometer. From this we can deduce, since the circumference will be 4 times this distance, hence the circumference of Earth will be 40,000 kilometers. Other units of measurement given are 1 kilometer is 3280 feet, or 1 meter is 3.28 feet. Statute mile is 5280 feet. Now we come to a nautical mile. Nautical mile by ICAO definition is 1852 meters, and its standard length is 6080. Now we come to the measurement of a nautical mile, or the derivation of a nautical mile is not very important, but this fact that 1 minute of latitude is 1 nautical mile, and 1 degree of latitude, which is 60 minutes, is 60 nautical miles at the equator only. So what this tries to say is 1 minute is equal to 1 nautical mile, and 1 degree equal to 60 nautical miles. And from this we can deduce that this distance, the distance between the pole and equator, will be 90 degrees, that is 90 into 60 equal to 5,400 nautical miles. Similarly, our circumference of Earth will again be 4 times this, that is 21,600 nautical miles, and half the circumference would be 10,800. The next topic is the variation in the length of a nautical mile. We all know that the Earth is an oblate spheroid and not a perfect sphere, so it is flatter towards the poles and more curved at the equator. So 1 nautical mile, that is 1 minute of arc, will be flatter at the poles and hence have more distance, and similarly 1 minute of arc will be curved at the equator and hence have less distance. So therefore a nautical mile is longer at the poles, that is 6108 feet, and shorter at the equator, that is 6048 feet. The average of this is 6076.1 feet, which for calculation purposes is taken as 6080 feet. Next thing we arrive at is the geocentric and geodetic latitude. Geocentric, as the name suggests, is a line joining the center of the Earth, which is an oblate spheroid, and a point on the Earth, and the latitude and is hence derived. For example, over here it is 45 degrees north. But for a geodetic latitude, what we do is we know on the surface a point is 45 degree north. We draw a tangent to that particular point, a tangent that only intersects the Earth at one point, and then we draw a perpendicular to this tangent wherever that line touches on the equator or plane of equator. This derivation is known as the geodetic latitude. The maximum difference between the geocentric and geodatic latitudes occur at 45 degrees north or 45 degrees south, which is 11.6 minutes. Now we arrive at certain examples given in the book. I'll just quickly summarize what to do in the particular cases. As in question number 1, it is given the shortest great circle distance between London and Accra both lie in the same hemisphere and on the same meridian. So you only need to apply the conversion factors, that is 1 minute is 1 nautical mile and 1 degree is 60 nautical miles. So over here we simply need to subtract the smaller latitude from the bigger latitude, get the difference, multiply, and arrive at the answer, which is given as 2689 nautical miles. In example 2, it is given same meridian and different hemispheres. So what we have to do in this is, whenever you have 2 points in different hemispheres and on the same meridian as is given in the question, you simply add both the latitudes. So in this question, we add the latitudes, apply the conversion factor, and get the answer as 5357 nautical miles. Example 3 states meridian and anti-meridian in the same hemisphere. So for this, what we'll do is we'll go over the pole. So for the first point, the latitude is 41 degrees 55 minutes north. We will find a difference between the north pole, that is 90 degrees, and this point, that is 41 degrees 55 minutes north. Similarly, on the other side, the latitude is 21 degrees 17 minutes north. We will find the difference between the north pole, that is 90 degrees, and 21 degrees 17 minutes north. We will add both the differences that we get, then use the conversion factor and arrive at the answer, which is given as 7008 nautical miles. These are pretty standard things to do. Summarize the first three. If you have 2 points in the same meridian, same hemisphere, you simply add latitudes. If you have same meridian, different hemispheres. So to summarize the first three examples, if you have 2 points on the same meridian and same hemisphere, then you will simply subtract the smaller latitude from the bigger latitude. If we have 2 points on the same meridian, different hemispheres, you simply add both the latitudes. If you have a meridian and anti-meridian in the same hemisphere, you will go over the closest pole, that is either the North Pole or the South Pole. Example 4 given is meridian and anti-meridian different hemispheres. So over here, you will need to ascertain whether it is closer to the North Pole or the South Pole. Easiest way to do that is take any one of the two latitudes and just change its hemisphere. So for example, in the question it is given as 35 degrees 57 minutes north. Change it to 35 degrees 57 minutes south. That is the antipodal point. Now look at the second latitude, that is 22 degrees 10 minutes south. So it is north of your antipodal point. Hence you will go over the North Pole. If the second latitude was given to be more than 35 degrees 57 minutes south or southwards of 35 degrees 57 minutes south, you will have to go over the South Pole. And use the conversion factors, get the answer as 9973 nautical miles. For example number 5, we have 2 points on the equator. This is just again the simple calculation, the same as the meridians, where 1 minute is 1 nautical mile, 1 degree is 60 nautical miles. So over here we need to find the distances between two longitudes that are given as 16 degrees 35 minutes west and 103 degrees 55 minutes east. You will simply add both of them together and arrive at the conclusion, which is 7230 nautical miles. The sixth example is a special case where we have exactly antipodal points. That is, the first one is 51 degrees 30 minutes north latitude. The second one is 51 degree 30 minutes south latitude, and they are on meridian and anti-meridians. Over here, what we will do is simply find out the semi-circumference of Earth, which we know the circumference is 21,600 nautical miles. The semi-circumference would be 10,800 nautical miles, which is the answer. The mean latitude, which is the next topic, is simply adding both the latitudes and dividing by 2. If you look at the questions given in the textbook, question number 1, what is the change of latitude? Again, for A, you will subtract the smaller one from the bigger one. For B, you will have to add both of them together since they're in different hemispheres. For C, again subtract the smaller one from the bigger one. And for D, you will have to find the difference between each pole or each latitude and the North Pole. So 90 degrees minus 71 degree 20 minutes north and 90 degree minus 86 degrees 45 minutes north. Add both of them together to get the change of latitude. Question number 2 is what is the difference in nautical miles and in kilometers from position A 41 degrees 25 minutes north to position B 79 degrees 30 minutes north. Both are in the same hemisphere. So we will simply subtract A from B, arrive at the answer in nautical miles, and use the conversion factor to arrive at it in kilometers. Question number 3, what is the change of longitude between the following positions? So again, using the same concept as that of latitudes, for A, you will subtract the smaller one from the bigger one. For B, since they are different western and eastern hemispheres, you will add both of them together. For C, since it is closer to the 180 degrees anti-meridian, you will find the difference from each point and the anti-meridian and add them together. And for D, again same. For C, again subtract the smaller one from the larger one. And for D, the closest common point is the anti-meridian. So we'll have to find the difference between the anti-meridian and each longitude and then add the differences together to arrive at the answer. Question number 4, give the direction and change of latitude and longitude from x to y in each case. Using the concepts from above, if it is in the same hemisphere, then you will subtract. If they are in different hemispheres, add. If they are closer to either pole or either anti-meridian or meridian, then you will find the difference from that particular pole or meridian, anti-meridian. Add them together, arrive at the conclusion. And the direction can simply be found using common sense whether you're traveling eastwards or westwards. Question number 5, give the shortest distance in nautical miles and kilometers between the following positions. We will use the same concept as discussed earlier. Question number 6, an aircraft is to fly from position 72 degrees north, 2 degrees 30 minutes east to position 72 degrees north, 177 degrees and 30 minutes west. Since this is the antipodal point in terms of longitude, we will be going over the North Pole and not around the Earth, since it is the shortest possible route. So for question A, give the initial true track direction. Since we are going to fly over the pole, our initial direction will be polewards, that is 000 or 360. Question B states, will the track direction remain the same for the whole flight? The answer is no, since once you pass the pole, you will be flying southwards, that is on a direction of 180. And the reason for the same is question number C. Give a reason for the answer. Question number 7. You are at position A. You are given the change in latitude and a change in longitude. You just need to calculate the position B. That is given the if the change in latitude is westwards, then you will subtract. If it is eastwards, then you will add. Question number 8. You are at position C Add given coordinates. Again, the same change in lat and change in long is given. Arrive at the answer. Question number 9. What is the position of the rhumb line between 2 points relative to the great circle between the same points if the points are in the northern hemisphere? Since we saw in the diagram earlier, right here, in the northern hemisphere, the rhumb line will be southwards or closer to the equator, and in the southern hemisphere again the rhumb line will be towards the equator or north of the great circle. Question number 10. Any meridian line is a. Option number A is rhumb line. Is any meridian a rhumb line? Yes, it is. Option B, semi-great circle. Any pair of meridian and anti-meridian is a great circle, but just the meridian, which is simply the half of a great circle, is a semi-great circle. So option B is right as well. Option C states rhumb line and a semi-great circle. Hence, option C is the most suitable answer. Question number 11. A rhumb line cuts all meridians at the same angle. This gives. Question number A is the shortest distance between 2 points. This is incorrect since we saw that the great circle track will give the shortest distance between 2 points. Option B is a line which could never be a great circle track. This is not the case since the equator as well as a pair of meridian and anti-meridian is both a rhumb line and a great circle track. So hence option B is incorrect. Option C, a line of constant direction, is the correct answer. Thank you for tuning into this chapter. We'll be back with more in the next session.